This video is about enthalpy of reaction. By the end of this video, you should understand what enthalpy of reaction measures, and you should be able to calculate enthalpy changes for processes using the balanced equation. Prior to this, we've been looking at energy changes associated with phase changes and with heating and cooling. Enthalpy of reaction refers to the energy change during a chemical reaction. It's often abbreviated delta H Rxn, or just delta H. You may also see delta E. For our purposes, this can be used interchangeably with delta H. The enthalpy of reaction is the sum of the energy required to break the bonds in the reactant molecules and the energy released in forming the bonds of the product molecules. As we know, in order for a reaction to occur, energy must be put in to break the bonds in the reactant molecules, and energy is released when new bonds form in the product molecules. The enthalpy of reaction is essentially the net energy change of this process. The enthalpy of reaction is essentially just the enthalpy of the products minus the enthalpy of the reactants, or the final energy state minus the initial energy state. Some important things to be aware of about the enthalpy of reaction. First, it's proportional to the amount of reactant consumed. This means there's a stoichiometric relationship between moles of reactant and energy change. As we said before, it's the result of the difference in energy required to break reactant bonds and the energy released when new product bonds form. And it depends on the phase of the reactants and products, whether they're in a solid, liquid, or gas state. When looking at the energy change for an exothermic reaction, we see that the reactants are higher in energy than the products. Therefore, the energy released when the product bonds form is greater than the energy put in to break the reactant bonds. Therefore, there's an overall decrease of energy in the system. Thermal energy is released, and our sign on delta H is negative because energy has exited the system. For an endothermic reaction, on the other hand, energy is gained or absorbed by the system. This is because the energy released by forming product bonds is less than the energy needed to break the initial reactant bonds. Therefore, more energy was put in than was released. So overall, we get energy absorbed by the system, making our delta H positive. When a reaction is manipulated, we can also consider the enthalpy change associated with it. For example, if we reverse a reaction, the sign of delta H is reversed. In other words, the amount of energy that goes in for the forward reaction is the same as the amount of energy that comes out in the reverse reaction, or vice versa. Looking at an example here of an exothermic reaction, if we reverse this reaction, the magnitude of the enthalpy change is the same, but it's opposite in sign. The energy is gained rather than released. Likewise, the magnitude of delta H is directly proportional to the quantities of reactant and products. For example, if you make twice the amount of product, you will release twice as much energy. Using the same reaction as we saw above, here we've doubled the reaction, therefore we've doubled the amount of energy released. For this reason, we can perform stoichiometry calculations with delta H's. Take a second and solve this problem on your own. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice that according to our balanced equation, every 2 moles of hydrogen gas with excess oxygen will release 570 kilojoules of energy. Therefore, 25 moles of hydrogen gas should release 25 times that amount of energy. That brings us to the end of this video. Let's review our goals. First, we looked at what is meant by the enthalpy of a reaction, and then we looked at how to calculate enthalpy changes for processes using the balanced equation.